Hey class, this is Mr. Schmidt for Environmental Science. We're talking about uh, Monday, February 8th, weather overview 9.3. And let's get right into it here. The opening question was, what is El Nino? And we talked about that earlier on the last video. El Nino is the warming of the Pacific Ocean off the coast of Western South America that occurs every 3 to 10 years. And that added energy of the ocean dramatically alters the weather, the global weather patterns, especially off of the west coast of North and South America. So opposite of El Nino is they call La Nina, which occurs when trade winds on the Pacific are unusually strong and the equatorial ocean surface temperatures become cooler than normal. So El Nino, it's warm waters and greatly disrupted weather patterns, and La Nina is colder water, which gives much milder weather patterns. Okay, so that brings us to our weather overview. It's a good week to talk weather as we're going to have some cold fronts pushing in this week, and we can talk about fronts here today as we'll be able to research and discuss some of the underlying properties of weather. So first of all, let's make sure we're clear. Weather is a description of the current state of the atmosphere. It's caused by interactions of air and water and sunlight, okay? And it is measured through temperature and pressure and humidity. So the big thing to pull off of this page is it is the current state, okay? Climate, we're going to talk long averages, like 30 years over large sections of land. Weather is what's happening right here, right now. So like I said, a few things are going to be used to measure weather. The first one being temperature. Temperature is a measure of the average amount of motion of the molecules. So I'm sure you're all familiar with what temperature is, but when you get down to the smallest measures, the air particles, all that nitrogen and oxygen and so on is bouncing around. That's what carries energy from one place to another in our atmosphere. So when it's cold out, those particles don't move very much. And if we got down to negative 273 Celsius, it wouldn't move at all. Okay, but as it heats up above negative 273, above absolute zero, it eventually gets more and more motion. And all those particles all moving give us what we know as temperature. Okay, now if we were looking at what is the temperature of a specific place, it's going to depend on the latitude. Okay, how far north and south it is, because that's going to tell us and affect how much solar radiation is striking the Earth at that place, how directly sunlight is hitting it, and the total amount of radiation that reaches the surface here. Okay, next measure is the air pressure, which is how much force the air is pushing on all surfaces. So if you think about a balloon, you pump up a balloon, it gets more and more pressure, okay? And it's more force is being applied to the sides of the balloon. All right, this is also true for the atmospheres. When the air is heated, okay, we have all those particles moving all over the place. They have lots of energy. They create more space in between the particles. They become less pressurized, okay? They begin to rise. And the cold air will come in beneath it. And so we see the temperature playing differences with the pressure as the high pressure, low temperature pieces want to come in below, and the high temperature, low pressure tends to rise up. Okay, and then the third piece of all this is humidity. Humidity can also affect pressure, and it can affect how we experience temperature, and temperature affects how much humidity can be held in the air. Right now, we're going to focus on humidity as the amount of water vapor in the air, and the relative humidity, the measure of the amount of water vapor compared to the maximum amount, the saturation amount for a specific temperature. Okay, there's other ways we can measure humidity, but right now we're going to focus on this one, the relative humidity. If you can hold so much based on where we are right now, it's 65 degrees Fahrenheit. So this is how much water can be held in the air. Did we reach that to 100%? We did this morning when it was all foggy out and we're getting covered in dew. Okay, or this afternoon when it's all sunny, temperature went up, it could hold more water, but there's very little moisture in the air and everything dried out. Okay, so now we start putting all these pieces together and we get air masses and weather fronts. So an air mass can be a polar or tropical, continental or maritime. So we've talked about those before. We have all these different ways we can look at where is it coming from, how is that going to affect the source, will affect the temperature, pressure, and humidity. So that air mass is going to be a large volume with that uniform moisture and temperature throughout. Okay, and as we look at this air mass, as it moves across the planet, across the surface of the Earth, it's going to bump into other things, into other air masses, and those areas of collisions are the weather fronts. So we'll see warm fronts and cold fronts, and we can kind of predict based on their name what kind of weather is going to appear after it passes through. And we can also look into more detail. As one shows up, we can predict a number of different things are more likely to occur, which is how we can make weather predictions. Okay. By the way, there's also occluded fronts. We're not going to cover those just yet, but if you go ahead and Google some things, you're going to find out there's more than just a warm front and a cold front. Okay. So we have these different pressure systems, and that's going to create wind. So wind is just the air moving in a specific direction, but any specific direction it has to be horizontal. Okay. If we have air moving up and down, those are air columns, and that's going to be something different. The horizontal motion is the wind. And the wind begins with differences in air pressure. So we have high pressure one place, low pressure somewhere else. The air is going to try to move from the high pressure to the low pressure, and that's when we experience the wind. Okay, so remember, we have all these different temperatures and pressures set up because the Earth's at a tilt, it's spinning, it's getting different temperatures throughout the different seasons. So these pressures are always shifting, and it's always driving the winds across Earth. All right, next up we see fronts. So we had these warm fronts and cold fronts, or high pressure areas and low pressure areas. So if we have a cold front, then the cold air is coming in, and it's cold, it's dense, it's heavy. So it comes in and it forces the warm air up. The warm air is trying to stay still, and the cold air will come in and force the warm air up, and that will, the warm air, it's warmer, it's less dense, it can hold more moisture, but as it rises, it's going to get colder, and it's going to hold less moisture, and that's when we're going to start seeing some of the rains, okay, from a cold front. Okay, and because it's going straight up, we get these cumulonimbus clouds, okay, and we get thunderstorms, and that always happens at the beginning of cold fronts. Okay, warm fronts, the cold air is moving out, and the warm air follows it, takes in that open space. Okay, again, when that warm air hits the cold air, it's going to drop the moisture, and you're going to get much lighter rains or a constant rain. So we see that fairly frequently around here. Okay, more looking at humidity and temperature. So we see this a lot of mornings. During the day, the air got warm, it could hold more moisture. At night, the temperature goes down. It cannot hold as much moisture in the air, and we get dew. We get little pieces of water all over the grass and all over your windshields, and that's when the temperature dropped below the dew point. So the air is cooled, and has received or achieved the relative humidity of 100%. Okay, so that's what we know it's hitting 100% because it starts sticking to all the grass and everything. Okay, the other thing that can happen, again, something that happened this week, the temperature drops overnight. Overnight, we had a lot of humidity and it's different special pressure in the air. So it didn't all just stick to the grass, but it formed clouds or fog. It forms water vapor, and that water vapor then is going to condense around dust or other particles, possibly freeze into tiny droplets or crystals, and hang in the air. Okay, so especially around Skyview and around Salmon Creek, we see a lot of fog forming along that creek bed. Okay, so that fog is just same water vapor, condensed and frozen, just like we see in the clouds. Okay, it's the exact same physical manifestation, it's just at different altitudes. So that tells us a little bit about cloud formation. We have sunlight's coming down, it's hitting the ground, it warms up the ground, which warms up the air, which warms up the moisture. That warm air can carry a lot of the humidity and the moisture up, and it starts rising as the warm, low density air comes up. But as it rises, it hits colder and colder air, and it is less and less able to hold the moisture. And so it condenses, and we get those droplets forming into clouds. Okay, so it can form all kinds of different clouds. This is not even the complete list of all the ones we can see and can document and can predict. But like I said, when we see these fronts colliding, if it all happens at once, we have these cumulonimbus clouds, which is very rare for us to happen around this area. These great big columns of moisture, and all those water particles and droplets and crystals are running into each other and forming static electricity, and it'll form lightning. Okay, so that's, if we know a certain front is approaching and we know it has a certain amount of energy and a certain amount of moisture, that's when they can predict cumulonimbus clouds, thunderstorms, lightning, take cover. Okay, so this is how they start making some of those predictions based on those measurements of temperature, pressure, and humidity. Okay, what we see around here is a lot of cumulus clouds or even stratus clouds, just a lot of low hanging clouds with moisture, but not the energy and the huge column of moisture that we see, maybe in the Midwest or Florida, when there's a lot of air moving and it's picking up moisture off the ground and it's colliding with other air masses. Okay, so we have these clouds. We know it can do things like form thunder and lightning. We know it's holding a lot of moisture, and it can drop that moisture in a number of different ways: rain, sleet, snow, hail. Okay, and this is going to be something we're going to track a lot this week, is what can we use to predict whether it's going to be sleet or snow or hail, and what's really the difference between these things. Okay, so it's going to depend a lot on the wind and the air pressure and the temperatures and where different temperatures exist within the atmosphere. So if I look at this picture from NOAA, from the National Weather Association, or Oceanographic and Atmospheric Association, what we see, if we start on one end with the warmest air, we get cold clouds dropping their moisture, it hits warm air, it turns into rain. That happens all the time, especially around here. Okay, well, what happens if it goes through warm air and then at the very end it hits some very cold ground or very cold air right at the very bottom? Well, then it's going to start freezing. Okay, and that can be a very dangerous situation as it freezes to highways, freezes to power lines, and you get this freezing rain. If it goes through warm air and then it hits cold air, it can be very dangerous. Okay, does not happen too often around here, but it definitely can happen, and it's worth paying attention to, especially if it's predicted. Okay, the next one can occasionally occur. It starts off in the cold clouds, hits a little bit of a warm patch and starts to melt, but then it refreezes right away, and we get kind of this mushy, slushy sleet. Okay, and that I've seen fairly often here. Just you're like, oh, maybe it's going to snow, but instead it just kind of splatters to the ground as just a little too warm for it to all occur. Okay, but not so cold that it turns into ice. Okay, and then the one we're all looking forward to, especially those skiers in the class, okay, is if it starts off cold in the clouds and stays cold, 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 and hits all the way to the ground, then we have some snow. We have something we can ski on, we can snowshoe, we can throw out a little brother, we can have fun with. Okay, so that's something maybe we'll see this week. Maybe you'll go up in the mountains and you'll get to see it. Okay, that's snow. So the one we haven't discussed yet is hail, because hail does not follow this top-down structure. Okay, hail starts up here, starts falling as rain or possibly snow, okay, but then there's an air column that blows it back up. So if you have some warm air coming up into the clouds, that's going to push the moisture back through the cloud, and it's going to freeze again. And it'll get pushed back up, and it'll get another layer of ice and another layer of ice until it's so heavy it can fall through that air column and hit the ground. And you can get baseball-sized chunks of hail if the air column is moving fast enough and applying enough force. Okay, so this is a form of precipitation that consists of solid ice that forms inside the thunderstorm updrafts. Great. So that was it for my lecture. I just wanted to point out you guys are probably experts at green screens by now. If you wear a green shirt on a green screen, looks like your clothes disappear, or you disappear, and you become the weather. So with that, let's take a quick look at the assignment. Okay. So again, we're going to start with weather is caused by an interaction of. And again, I'm not really concerned about which of these you put in which order. So it's going to be an interaction of the sun, the air, and the, do we have the surface? We could say water, which forms air masses. Okay, and then from there you can keep going. If we have questions, I will hopefully take them all tomorrow during storm time when I'll see you there. And with that, have a good night.